hitting record right now, so if you want to, if you feel the urge to kill your camera, go ahead in case you don't want to be on the YouTube video. That's fine because I'm going to upload it. It's up to you. Just going to give you a heads up. So I don't care. But anywho, to those of you who are watching on YouTube, hello. I hope you're all doing well. We're just talking about the importance of OChem. So the first 1/5 of the class, you learn about nomenclature. And that is going to be something that is going to be ongoing as you take the entire year of organic, because you're going to learn new functional groups, and those have new names and how you name things and all sorts of stuff and all that good jazz. So nomenclature, make it a commitment. Now it's going to keep coming back and back and back. Every exam you have is going to have nomenclature questions like, here is a molecule. What is the name? That is a very common thing. Next thing is molecular orbital and understanding why things react the way they do. This is probably the hardest part of organic. Once you get past it, it is easy. You just have to understand the physical chemistry aspect of why do things react the way they do. And it's all tied to the shape of their orbitals and stuff like that. All right, so I'm making a video for the last part of last week. So I'm going into the second week notes, and then that way it'll all be on YouTube. So if you go to YouTube, when you go to those links, you can just like subscribe to my channel, because there's going to be a bunch of YouTube videos on there for stuff. If you look around, you're also going to see YouTube videos for things like analytical chemistry and other stuff. So you can ignore those, because those are graduate level classes that I teach at Grand Canyon still. So if you feel the urge to, knock yourself out, don't let me stop you. Do you guys have any questions so far about organic chemistry? Anything that is like bothering you right now?
I don't have any specific questions.
Okay.
Yeah.
So, oh, go ahead.
Oh, I was just gonna say, for me, I think it's like orbitals. Like that got a little bit confusing. Like now I kind of understand them more. But I guess like when she made them like drawings and like the actual structure of them actually confused me a lot. I don't know why, because I honestly always skipped that in Gen Chem because I didn't think it was that important to like the reading. So yeah.
Okay, well, I'll just go back to the first week. So if you've watched the video so far, we'll just go back into the orbital diagrams and we'll start talking about that, because that is actually probably important. So I'll just go into this. And again, if you guys have questions, just throw it into chat or whatnot, or raise your hand or whatever, or unmute yourself. There's only a few of you, so I don't really care. So the important thing, if you remember, is that you got to know our orbitals. So in organic chemistry, most of our business, can you see my mouse?
Yeah.
Most of our business is going to be starting at boron through fluorine all the way down to iodine. Hydrogen, of course, is going to be popping up. And then we're going to see aluminum, silicon, phosphorus, and sulfur every now and again. And then a couple of the metals, lithium, sodium, potassium. But everything else is going to be over here. So most of our chemistry is going to involve the S and P orbitals. D orbitals are important, and they do come into play very later on, but kind of. And F orbitals are really just not involved in what we're doing. So really, it's the S and P orbitals that are going to be the bread and butter for us. So continuing on with this, so you can see here, this is basically the idea of our three most important orbitals. So we have 1s, 2s, and 2p, right? So for carbon, if you remember, I'm going to ask you this question. This is something we talked about. Do you guys remember hybridization? We talked about that last year. It's the idea of taking our S and P orbitals and combining them together to make a new one. So I'm going to ask you a question here, and I'm going to draw something. So imagine I have methane, which is CH4. All of those carbon-hydrogen bonds, do you think they're the same, like in terms of like they're the same energy and same reactivity? Like is there any difference between each of those carbon-hydrogen bonds? Do you think they should be the same? Yes or no?
Yeah.
Yeah, so they are going to be all the same, right? There's no difference because they're all carbon to hydrogen. There's no difference between them, right? But if I was to fill up my electron orbital for carbon, right, you go 1, 2, 3, 4, 5. 6. Now, if you notice, right, we care about what's in the red box because of our valence electrons. So the electrons in the 2s orbitals are in a lower energy than the electrons in the 2p orbitals, right? So the way that these orbitals are arranged right now, they're different energies. And when we form bonds, if covalent bonds, right, remember you donate an electron, so 2 atoms are sharing 2 electrons. So right now, carbon has 2 paired electrons and 2 unpaired electrons. If we just went with this theory, this would imply that carbon only wants to make 2 bonds, but we know that that's false because we literally have this molecule here called methane, which is in a lot of your homes as natural gas. So something is happening to these orbitals. They have to rearrange themselves. And this is the idea of where our hybridization comes in, if you remember. So real quick, taking a step back, we want to talk about the actual shapes of orbitals. So are electrons moving or are they just kind of stuck? What do you guys think? Are they like parked in place or are they always moving? They're always moving, right? And this is one of the, when you think back to physics, I know you guys talk about physics all the time, but one of the main problems with our understanding of physics is that we had to come up with this new idea called quantum mechanics because the regular like Newtonian physics just didn't work at this level. So basically, when we say, where are the electrons, we can't predict where they are. Have you guys ever heard of the Heisenberg uncertainty principle? Has that ever come up in your physics class or other stuff? It's essentially the idea that due to the unique nature of the molecule, its size and energy and all this stuff, you can't predict where they're at. I can either tell you their location or their momentum. I can't tell you both. And that's just one of the weird characteristics of quantum. Just know that. So the idea is that I can't tell you where an electron is, but I can predict where they're going to be. So imagine this right here, all those little dots. These are all where you would find electrons. This is where you're most likely to find them. And so when we draw our orbitals, we are saying that is where 90% of our electrons are found. Like 90% of the time, if I said, Melissa, where's an electron? You would say inside that red bubble. 10% of the time it's outside, like maybe just outside of it, like an electron could be here or here or here, but that orbital is just a probability. And that's just fancy nomenclature. This won't come up too much, but you just need to know that when we say an orbital, that's where we're most likely to find our electrons. And remember, in organic chemistry, electrons are what actually does the chemical reaction. So in order to predict reactability, you have to know where the electrons are. And that's what orbitals tell us, is where the electrons are going to be most likely. Does that make sense? How are you guys dealing with that? Okay, so these are what the s orbitals look like. Remember 1s, 2s, 3s, 4s, 5s, right? They're all the same shape. They just get further and further and further and further away from the nucleus. This is what all your p orbitals look like, all right? So you basically have, it looks like a bowling pin kind of thing. So these are just 2 different phases. And this is what all of the p orbitals look like. And so going on with this is that if you see here on this little axis, you will notice that we have this line where there are no electrons, and we call that a node. And essentially this means that you will never find an electron at that center point. So you can either find it to the left or to the right, and this is what we get is our 2 phases of our p orbitals. And that's it. That's all you need to know from this. We'll come back to the idea of nodes a little bit later, but just know that they exist. So you basically have, you can find the electrons on this side, you can find the electrons on this side, but you can't find them in the middle, you never will. And this goes into predicting reactivity again, but don't worry about that too much. So we have these 2 lobes that come together and it looks like a dumbbell or whatever shape you want to call it. And so electron density is 0 at the nucleus, and that's it. So 2 lobes have opposite phases. So you can think of it as being filled or unfilled. And again, this is going to come back a little bit later, so don't worry too much about it. We'll go a little bit more into depth in it. And so for 1s orbitals and 2s orbitals, right, we just have that sphere. We have this weird dumbbell shape in the x direction, in the y direction, and the z direction. So px, py, pz. So we have 3 p orbitals. And so on the right-hand side there, right, you will see that we have our 3p orbitals. So you have x with the red, y with the blue, and z with the green. Okay, so they're all just stacked on each other. And so this means that if you have your reactivity, right, this allows us to think where the orbitals are when they react. So this is it, nothing fancy. So now, as I move this out of the way, these orbitals work well to represent individual atoms. So When we talk about atoms and we think about just atoms in and of themselves, a carbon atom, a hydrogen atom, stuff like that, all we care about is the fact that they are just like the order in which they are. And so it works really well for that. It's pretty easy to do. But now once we start thinking about molecules, then it becomes more of an issue because it's really hard to take those basic orbitals and then describe molecules. So we've got to be a little fancier. And so we can think about structures simply in terms of Lewis dot structures with lines for bonds and dots for non-bonded electrons, like remember if we're doing our Vesper. But they don't give us a good picture, right? They don't show us what's actually happening because those bonds are in the correct angles. They are showing like the 109 degrees between each bond. They show the correct 3D shape, but it's not drawn correctly, meaning you're not actually seeing what the orbitals are doing, right? You're not seeing how the orbitals are aligned or anything. We're just drawing a bond between them and saying, this is where electrons are found. And so this is why we care about this. And so when we use Lewis theory, and this is something I did talk about last year, is that there are two things where Lewis dot structures fall apart. One, they don't give you the proper 3D shape. And two, they don't do resonance well. Do you remember doing this where we had to draw like the different resonance shapes of all the stuff, right? Lewis dot structure just doesn't make it easy. So here, when we draw this, we have 1, 2, 3, 4, 5 different resonance structures, which is very unwieldy. Like that is just not great to draw. And so these Lewis dot structures just are not great for doing resonance. They're not great for showing the correct 3D representation. So this is why we need a little bit better theory. And so this is why this is probably just a little bit confusing, is how do we make the transition from atomic orbitals to molecular orbitals or bonding orbitals? And this is what we did talk about, is that when we're bonding, we're sharing electrons. So since electrons are found in orbitals, right, when they overlap, when that space overlaps, that's when we can form bonds because now the electrons are coming together. They're in the space that they're occupying. So each orbital that we have, so 1s, 2s, 2px, 2py, 2pz, 3s, so on and so forth. Every orbital, if you remember, can only hold 2 electrons, right? So when we overlap orbitals, like an orbital from carbon and an orbital from hydrogen, just as a quick drawing, right? If you think about carbon and we think about an orbital overlapping and hydrogen with an orbital overlapping, like that, each orbital is the carbon orbital is gonna bring an electron, the hydrogen orbital is gonna bring an electron. So when they overlap now, we're gonna form a bond. And that is what's going to give us our 2 electrons in our orbital. Does that make sense? Are you guys on board with this? Are you feeling a little bit better? Okay, any questions right now on this while we're here? I know that this is still early going, so don't sweat too much. If this is this is the time to ask, right? I'm friendly. I like to think you guys are here, so this isn't as intimidating as asking in class. So definitely make this the time. All right, so going on with this now is that way there will be 2 electrons in the overlapped orbital, which is what we want. And so we will refer to each of these orbitals as being half filled, right? So if it has 1 electron, right, half filled. Okay, have you guys done this? How are you guys with MO theory? Are you okay with this? No or not? Okay, I see Matthew furiously typing into the chat, so I will read what he has to say here in a second. Maybe not furiously typing. Maybe he's just typing like 1 word. Okay. So this right here, this is from your week 1 notes, but we'll just start dipping into this. So I will give you, so the simplest example of atomic orbitals overlapping is to form orbitals to overlap to form H2. So if you remember, hydrogen is one of our diatomic atoms, right? So have no fear of ice cold beer. Hydrogen is one of our few diatomic atoms. And so each hydrogen, if you remember, has 1 electron. So my hydrogen has a 1s electron, and my other hydrogen has another 1s electron. All right, so when they come together, right, how many orbitals together do my 2 atoms have? When I combine them, how many different orbitals are they bringing to the table together? 2. hydrogen is bringing the 1s orbital, right, that it has, and the other hydrogen also has another 1s orbital. So now they have 2 orbitals, right? So in my little happy drawing, one hydrogen has an electron in its 1s orbital. The other hydrogen has an electron in its other 1s orbital, right? And now they are going to come together to form a bond. So I have 2 orbitals, right? I have what is called the bonding orbital, where my electrons are actually going to be at. And then I have the anti-bonding orbital. That's where the electrons are not bonding. So does that make sense how I'm using one of the orbitals to be my bonding orbital? That's where my electrons are. And then there's the anti-bonding orbital, the one that's not being used. There's no bonding going on there. Does that idea make sense with you guys? So the more anti-bonding, correct. So this is something that you'll do a little bit later in terms of calculations, and I don't want to do it for right now if you don't have to learn it. But basically the idea is, if you just have bonding orbitals filled, it'll be more stable. Once you start filling in those anti-bonding orbitals, they become less stable. So right now, since you just have 2 electrons in your bonding orbitals, you have what type of bond? What type of bond? Since you have 2 electrons that are being shared, as I stretch my back. A sigma, you have a single bond. That's correct, right? Because you're just sharing 2 electrons. Does that make sense? Right? So a sigma bond, you share 2 electrons. If you have a double bond, you would have a sigma and a pi bond. If you had a triple bond, you would have a sigma, a pi, and another pi, right? So then you would be sharing 6 electrons. So as you go up, this will get a little bit more not complicated, but just more stuff on it. But this is why hydrogen's a really good example, because it's our simplest diatomic. It's our simplest molecule that exists in the universe. So if we just remember we were bringing 2 orbitals in together, we can combine those 2 orbitals like this. And then, we get our bonding and our anti-bonding. That's just the basic idea of how this works, right? If you go up into inorganic chemistry, you are going to learn a lot more about this. So I don't know if any of you are chem majors, but if you do go into inorganic, you'll learn a little bit more about this, but it should make more sense by the time you get there. That's the goal. All right, so what are bonding and anti-bonding? So remember, electrons have a particle and a wave nature. So if you remember, electrons are like really weird in that they are a particle. They are just this subatomic particle, but they also exist in a wave-like nature, right? They have wave functions to it. And so the picture of the wave nature of an electron is essentially a picture of the orbital, right? So we can think that we are either adding our electrons together in a constructive manner, or they are deconstructive. Do you guys remember sign like things from like trig, or if you took physics 1 where you have like 2 waves and they add up, that's constructive. Or if you have a wave that cancel each other out, those are destructive. It's the same idea. Since electrons have this duality of both being a particle and a wave, this is essentially what's happening. In our bonding orbitals, they are constructive. In our anti-bonding, they are destructive. So here you can see, right? So when they come together in the middle, right, those two waves, since they're on the same side, it's constructive right there. They add together, right? And this is the idea. This is constructive interference. Now, you can see when they come together here, when they hit, they cancel each other out because one's going up, one's going down, so that they cancel. So that's what's happening here, is that we have this destructive interference there. They are canceling each other out. Does that make sense? For the difference between constructive and destructive, right? And this is just based on the fact that electrons have this duality of being a particle with wave-like functions. It's just one of the quantum things you have to accept. No one's ever going to ask you to explain quantum mechanics in this class. You just kind of have to understand some of the basic ideas. For those of you that are chemistry majors, when you get to physical chemistry, you will have to explain the quantum side of it, but you will have a lot more math and physics under your belt at that point before you try to do that. So don't feel worried about it, unless for those of you who's like organic as far as you have to go, or some of you guys going further. Okay, if you have to go to organic and biochem, you're not going to learn much more than this. If you have to go, organic and biochem are about as far as this goes. It's about as dense as it gets. If you are a chem major and you go to inorganic and physical, then you're going to learn more about this. But PChem is actually kind of fun. If Garrett is still there, he's Lindbergh. Garrett Lindbergh is a PChem professor for those who have to take it, and he's really good. So I would recommend taking him when the time comes. So now we see this bonding and anti-bonding, right? And so also wire orbitals labeled. So this is our constructive, where we have our constructive here and our destructive. That's the idea. And so now we have wire orbitals labeled. Does anyone know what Greek letter this is? It's lowercase. You guys just told me a few seconds ago, well, a couple slides back, what type of bond is it? That is the Greek letter for sigma. So sigma star, right? And basically it's just the idea of our bonding and anti-bonding sigma orbital. So if you had a double bond, what type of orbital would you have if you had to guess? You would have a pi and a pi star. Yep. So you would have sigma, pi star, sigma star, right? You would have your sigma pi, and then if you had a triple, it'd be sigma pi star, sigma star, right? So that's basically what's going to have. And so a sigma bond is one that forms from head-on. Basically, your orbitals are overlapping. You have this constructive interference. And so this is what a sigma bond is. Your bonds are overlapping on top of each other, right? Like when I drew the carbon hydrogen, this is it. And so now, if you have the atomic orbitals of opposite phases, remember how like we had the red and the white? If those overlap, that's our destructive interference, right? And this is where you get your anti-bonding. So bonding, good. It's where our electrons are at. Anti-bonding, bad, not energetically favorable, all right? And so just think of bonding molecular orbitals as where you're going to find your electrons. Yep, and that makes sense because hydrogen only wants one bond, right? It follows the duet rule. It only wants 2 electrons, doesn't need 8. All right. How are you guys doing? That's probably really dense for you, right? Are you guys doing okay? This is coming out of this is always like I said, this is probably the toughest part of organic chemistry. If you can get through this section of material relatively unscathed, you'll be able to make it through the rest of it. And I promise you, anyone who is a pre-med major or pharmacy or other stuff like that, they will all tell you this part sucks. And this part, when it comes to things like the DAT, the MCAT, and other stuff like that, very rarely comes up, if at all. It's more about the reaction stuff. All right, so don't worry about this too much. Now, when you are when Jennifer Lewis is talking to you, make sure you pay attention because there will be tests on this, but this is just, you just need to understand it. So sigma bond, electron density is symmetrical about the bond axis. So if we think about our electron density, like if you turned it like from this way to look down it, that's what we're looking at. So that electron density goes straight down the center, all right? So you can imagine that we're just rotating that like this, so you're looking down the center like that, all right? All right, next up. So we have a basic idea of how to make bonding orbitals from atomic orbitals, right? We have this idea of our orbitals overlap. We have the bonding, we have the anti-bonding, stuff like that. The next thing though is figure out which atomic orbitals each atom has. In the case of hydrogen, right, that was the 1s orbital that was coming together. And then you make the atomic orbitals overlap to make bonding orbitals. And so the last thing here is the number of bonding orbitals will equal the starting number of orbitals. This is orbital math 101. So like I said, we have the hydrogen had a 1s orbital, the other hydrogen had a 1s orbital. So the sum of our bonding and anti-bonding orbitals was 2. However many orbitals we bring in is however many orbitals we'll have. Same with electrons. However many electrons we bring in valence-wise, that's how many electrons we can play with, right? So everything, this is the idea of numbers have to stay the same. We can't just get rid of stuff or add stuff. It has to come from somewhere, right? If the overlap is head-on, this is a sigma bond, all right? So looking at this here, get the little warning. In like 10 minutes, I'm gonna have to restart the meeting again just because I don't have the professional anymore since NAU took my credentials away since I'm no longer an instructor. But I'll just like pause it and I'll reopen it. So that'd be a good time to take a break and whatnot. So, you know, you guys can go get a drink of water and I'll keep lecturing when we come back. So then that's not a problem. So we have about 10 minutes left. And then it usually gives me like a minute warning. So I'll let you know when that's over and then everyone can go grab a drink of water, go to the bathroom or whatever. And then I'll finish up and do another part and I'll make sure to upload the lecture for the next part. So here in this wonderful little thing is let's try the simplest organic molecule that we're going to deal with, and that's methane, CH4, right? So CH4, our wonderful methane, there are 4 electron groups, each of which is a CH bond, right? So if you remember, CH4 is tetrahedral. Because carbon is our central atom, there are 4 electron domains, no lone pairs, so it is going to be tetrahedral for the electron geometry and the molecular geometry, all right? And so now carbon has 4 bonds, so it needs 4 atomic orbitals to bond. That makes sense though, right? Since for every bond, right, you need an orbital. So those 4 atomic orbitals in theory should overlap with 1s orbitals from each of the hydrogens to make new bonding orbitals, right? That makes sense because which orbitals does the hydrogen have access to? What is the only orbital that hydrogen has access to? It being our simplest 1s, right? Hydrogen will only ever have access to the 1s orbital. That's just because it only has 1 electron, right? And it's just sitting there at the lowest orbital level. So the 1s orbital, right, has to overlap with the carbon orbital, whatever one we're going to use in order for the bond to form. Does that make sense? Where our orbitals have to overlap? So in order for this bond to form, the orbitals have to overlap. The 1s has to come from the hydrogen, and something has to come from the carbon. But what exactly is coming from carbon? So let's take a look at this. What is wrong with this picture right now? And I kind of gave you the answer to this way back when. What is wrong with this picture in terms of our orbitals? They're not by one each other, which means that they're not what? What's our y-axis? Energy, right? So we just said, 20 minutes ago, you guys were younger then, more full of hope. Our orbitals have to all be the same energy, right? Because the carbon-hydrogen bond, they should all be the same. But here we have 4 orbitals. We have the 2s, right? We have this orbital, that's 1. We have a 2px, that's 2. We have a 2py, that's 3. And we have a 2pz, that's 4. So we have 4 orbitals, right? But they're all different energy, and that's right. I think that's, Bay just said that. Hybridization, right? Hybridization is what's going to allow us to put these at the same energy level. Because if they weren't at the same energy level, it would make no sense. And this is really what's going to allow us to do this. So promote 1 valence electron from 2s to 2p. Yeah, see now we kind of have, now it's a little bit better, right? So now it does look a little bit better in that we have everything. We have 1 electron per each orbital. Now each orbital can share. So this is better, but it's still wrong because our orbitals are not the right energy still. And so now if we did this, here you could see during our Lewis dot structure, right? It would be 90 degrees, and that's wrong. And so we have the 2s, right? So our 2s, this is all sorts of mess up. This is not happy. This is all sorts of wrong, right? Because if our 2p orbitals are coming out like this in the x, the y, and the z, that doesn't give us the correct bond order. And this is all just wrong. And this is still the hybridization, why we have to do the hybridization. We take our 2s and we take our 3 2p's and we hybridize them, and now we have 4 sp3 hybrid orbitals, right? And now they're all the same what? What is the key thing? They're all the same to your y-axis. Energy. They are all the same energy, and that is the key thing now. So now, since they are the same energy, we can better arrange them. This is very important. And now each orbital now has 1 electron. Each orbital is at the same energy level. Now they can all form the 4 bonds we need them to. So now when I make methane, each carbon-hydrogen bond is going to be the same energy because it's the same type of orbitals overlapping. Pretty much. But I taught you this hybridization stuff, right? I mean, I taught you this. And I told you back then that Lewis diagrams were just a means until it didn't work anymore, right? It's useful because it shows you how to connect things, but MO theory is just so much better. And like I said, these theories work until they don't. And then as chemists, not me, smarter chemists come up with better ideas and theories to explain things. Well, Lewis structures hated you too. I don't want to tell you, but they've been talking mad shit. It's a fun fact. All right, but that's just it. All right. And this is just the idea, right? This is a really fancy way to say that we need to do the hybridized orbitals. And so we mix them. And so this is a good question, why does carbon use hybrid orbitals to bond? Because it doesn't have enough orbitals to bond, because the overlap of carbon's atomic orbitals give geometries inconsistent with reality, and because carbon is an atom that makes for a bond. So really, it's just that, this is hybridization is a way to explain what we're actually seeing. Does that make sense? It's a theory, it's a molecular theory that allows us to say when carbon forms four bonds, if they're all sigma, they should all be the same energy level. And this is what has to happen for it to make sense, because we can't just pull orbitals out of the air. We have to combine them. And this is what a hybridization is, right? And that's all they're saying. Okay. Let's go in with that. And so now these sp3 hybridized orbitals, we now have them in this shape. And so now you can see it is 25% S character and is 75% P character, because we took 3 P orbitals and 1 S orbital. That's the ratio. And so if you now look, its shape looks more like a P orbital, right? Because you remember an S orbital was like spherish and the P orbital was like that dumbbell. And so one end of the SP orbital is round, but then it kind of tapers off. And this is why we have a hybridization. It combines properties of both. So it looks a little bit like S, looks most like P, and this is just a way to form our stuff. All right, so next question. How many single bonds will a carbon atom have if it is sp3 hybridized? How many? Go ahead and throw it in the chat. I got a D, got a 4. A 4 question mark. The answer here is that it's 4, right? Because how many orbitals did I bring together to form the sp3? I brought my S and 1, 2, 3 P's. So for every orbital I hybridize, that's how many sigma bonds I'm going to have. Does that make sense? So I'll ask you this. I don't know if this is on the next slide or not. How many sigma bonds would a sp carbon have? Two. Because I brought together 1 S, I brought together 1 P, right? So since I only combined 2, does that make sense? sp3 we said, right? Because we brought together 4 is going to have 4 sigma bonds, right? sp is going to have 2 sigma bonds. That's the sigma. I can't draw a sigma all that well. So then if I had an sp2 hybridized, how many sigma bonds would that have? How many orbitals came together to form this? An S, a P, and a P. So I'm going to have 3 sigma bonds. Does that make sense? So however many orbitals I hybridize, that's how many sigma bonds I'm going to have. All right. And so if you remember way back when, here is a molecule that you might remember. This is carbon dioxide. What is the hybridization of that carbon? Best guess. I just gave you 3 possibilities. sp3, sp2, and sp. What is the hybridization of that carbon? How many different things is it connected to? 2. So what is its hybridization? sp. Exactly right. So every bond, whether it's single, double, or triple, will always have a sigma bond like that. And I don't know why this happens sometimes, but it does. Okay, so now, when I hybridize my orbitals, I'm combining the S and the 3 P's. But in this case, right, for my CO2, I made an sp, right? How many orbitals do I have left that have not been used yet? What's left over when I made my hybridized orbitals? What's left? 2 what?